Okay, so today I'd like to talk about a paper written by Harikane et al. The silver rush V census of Lyman alpha, oxygen 3, hydrogen alpha, and carbon 2 line emission with around 1000 Lyman alpha emitters at a redshift of 4.9 to 7, revealed with the Subaru telescope. The problem this study wishes to address is that Lyman alpha emitters, which are a type of galaxy, were discovered to have a weak carbon-2 emission at a redshift of about 6 to 7. But other galaxies at similar redshifts seem to have way higher carbon-2 emissions. So there is a deficit between Lyman alpha emitters and other galaxies. And this deficit could be explained by lower metallicity in Lyman alpha emitters, because less carbon-2 means less metallicity. The goal of this study was to measure the metallicity and its correlation for Lyman alpha emitters. Another important implication of the results of this study could be for the ion efficiency in galaxies, because there currently is a disagreement between scientists that whether active galactic nuclei or faint star-forming galaxies would dominate the re-ionization in the universe. Lyman alpha emitters are frequently used to estimate ion efficiency, and so looking at a Lyman alpha emitter in the far out universe could tell us a lot about star-forming galaxies, because it's the early universe and lots of stars were formed in that time. So we could disprove either of the two hypotheses. The method used in this study is basically gathering data with telescopes as usual in many different filters for a lot of Lyman alpha emitters. So the images we got needed to be processed before we could work with them. The point spread functions of these images were very high, so the accuracy had to go up. Well, this figure shows how we got rid of the unwanted neighbor sources, which disrupt the picture. We basically first make a high resolution image and indicate where the excess sources are and let the computer remove them. And the result is a simple dot in the middle, which is the Lyman alpha emitter. And we had to do this for every filter. And in this way, we got a lot of... So we created 4 subsets at different redshifts to look at differences between distances. So what we do next is we stack all the Lyman alpha emitters with similar Lyman alpha equal widths, for the line equal widths, into a subset together, because they have very similar characteristics, so we can just put them all together and assume they're all the same. The individual differences and the contaminations they cause are insignificant compared to the already existing uncertainty in the project, so we can just get rid of those. Once we have all stacked images, we fit them to a model of the spectral energy distribution for a young star forming galaxy. And we do this by using all the filters and looking at color differences to estimate where the absorption lines should be. Well, this figure shows the best fit in black for some of the stacked images, with in gray the 1 sigma uncertainty. In this picture, the red open dots aren't used because the interstellar medium blocks out radiation in this wavelength too much. Results we got from this are basically that the closer Lyman alpha emitters have a higher H alpha equivalent width, and this would mean that they have a young stellar age or low metallicity, because a high concentration of hydrogen means a low metallicity. Lyman alpha equivalent width increases with the Lyman alpha escape fraction, so we show a correlation between the two. Important because the equivalent width to escape fraction ratio of a Lyman alpha radiation is proportional to the hydrogen alpha over ultraviolet emission, and this in turn is proportional to the ionization efficiency of a galaxy. Next, we compare all redshift subsets shown in the figure. The oxygen 3 over hydrogen alpha ratio increases with Lyman alpha equivalent width, but eventually we see a turnover and it decreases. So what a high oxygen 3 over H alpha ratio means is again a low metallicity, because it turns out that this turnover is caused by other factors such as age and ionization. Once we set these constant, we can see that the oxygen 3 over H alpha radiation ratio just keeps on going up instead of going down at the turnover point. Well, looking at the carbon 2 over the star formation ratio measured and compare this to the Lyman alpha equivalent width, we find the expected anti-correlation we talked about earlier. So this could explain the carbon 2 deficit that was. Well, to summarize the main findings, we have this figure. In black is the findings of the study, and in gray is the 1 sigma uncertainty. The other colors represent the other works, and as you can see, they agree very well, as they all lie in between, as they almost all lie in the 1 sigma uncertainty level. So the conclusions: hydrogen alpha equivalent width increases with Lyman alpha equivalent. A high hydrogen alpha equivalent width means that the galaxy we're looking at has low metallicity or is very young. The escape fraction of Lyman alpha radiation also correlates with the Lyman alpha radiation equivalent width and is independent of redshift. The carbon 2 over hydrogen alpha ratio and the Lyman alpha equivalent width are related. The Lyman alpha increases with decreasing metallicity, as we have seen, and once we relate the metallicity to star formation ratio, we can see what causes the carbon 2 deficit in the galaxies that have a high Lyman alpha equivalent width. So to summarize the findings in one sentence, galaxies with high Lyman alpha equivalent width have high Lyman alpha escape fractions, are metal poor, have a higher ionizing photon production rate, and have weaker